For decades, astronomy told a fairly comfortable story about Venus. It formed in the same neighborhood of the disk around our star as Earth did, close to the same size, close to the same mass, made from close to the same raw material. Two worlds born side by side, so alike in the numbers that we still call Venus Earth's twin. For a long time, that comparison felt almost reassuring, as if the planet next door was simply a warmer version of home, a world we would eventually understand just by understanding our own. Then we actually got a look at what was underneath the clouds, and the twins stopped looking anything like home. Underneath that cloud deck, the surface temperature runs to about 864 degrees Fahrenheit, hot enough to melt lead, and somehow hotter than the surface of Mercury, even though Venus sits twice as far from our star. The air at ground level presses down with something like 92 times the weight of our own atmosphere, close to what a person would feel standing 3,000 feet underwater, and the clouds above are made of sulfuric acid. Only a handful of machines have ever reached that ground and sent back an image of it. The Soviet Venera landers of the 1970s and 1980s lasted minutes before failing. And the longest survivor, Venera 13, held on for about 2 hours and 7 minutes before the heat and the pressure finished it. No spacecraft has photographed that surface since. The cloud deck that hides it circles the whole planet roughly every 4 days, at more than 200 miles an hour, and it has kept the ground essentially unseen from us for over 4 decades. What that ground actually is remains uncertain and heavily debated. Radar mapping from the National Aeronautics and Space Administration's Magellan spacecraft found rugged highland terrain called Tessera, and some scientists read it as the remains of ancient continents from a time when Venus may have carried its own oceans. Climate modeling out of the National Aeronautics and Space Administration's Goddard Institute for Space Studies has suggested those oceans could have stayed mild and stable for billions of years before a runaway heating event sealed the planet's fate. But a study published in Nature in 2021 argues Venus may never have had oceans at all, and no one knows yet whether that earlier, gentler Venus ever existed outside of a model. Then there is the cloud layer itself, where a detection of phosphine, a gas we associate with life, was announced in 2020 and then thrown back into serious doubt almost as fast. Whether that signal means anything at all is still argued over today. That is the real shape of the mystery we are about to sit inside. We have a planet next door, built from the same material as our own, that we have not actually seen beneath its clouds in over 40 years. And every clue we do have about its past points in more than one direction at once. If you stay with us through what the evidence actually says, and subscribe so you do not miss where this goes, we will get to the mission now being built to finally look again. A probe set to plunge through that atmosphere and photograph the ground itself for the first time since Venera. Something about Venus is still being withheld from us, and we are only beginning to find out what. Every number attached to the surface of Venus reads like a warning label written by someone who wanted to be believed. At ground level, the temperature holds at roughly 864 degrees Fahrenheit, day and night. At every latitude, because the heat does not come from direct light so much as from an atmosphere that will not let it leave. The air pressing down at that surface is close to 92 times what we feel standing at sea level on Earth, a weight scientists have compared to standing about 3,000 feet under the ocean, deep enough that ordinary machines built for open air simply fold. Above all of it, circling the whole planet, sits a deck of clouds made largely of sulfuric acid droplets, corrosive enough to dissolve most metals we would think to send down through them. We have only ever confirmed what that ground looks like a handful of times, and only because the Soviet Union spent the 1970s and 1980s trying, and mostly failing, to put a working lander on it. Early attempts were crushed or cooked before they finished transmitting a single frame. The longest survivor, a lander called Venera 13, held together on the surface for about 2 hours and 7 minutes before the heat and the pressure finished what they eventually finish with everything we send there. In that short window, it returned color panoramas of flat, cracked rock under an orange sky, the light filtered warm and heavy by the atmosphere above it, with thin slabs of stone lying broken across the ground, like something had shattered them from above rather than below. The mechanism behind all of this is not exotic. Venus carries an atmosphere made overwhelmingly of carbon dioxide, a gas that is very good at letting energy in and very bad at letting it back out. Earth's atmosphere holds a trace of the same gas and still warms noticeably because of it. Venus holds an atmosphere roughly 90 times more massive than ours, saturated with that same heat-trapping gas from top to bottom, and the result is a greenhouse effect that never lets the surface cool, regardless of how far the ground has rotated from direct starlight. It is, in the most literal sense we have measured anywhere in this solar system, a runaway version of a process our own planet runs in miniature. What we still cannot say with confidence is how that atmosphere got this way, or whether it always looked like this. That single fact sits underneath everything else in this story, because if we do not know how Venus became a furnace, we do not fully know what protects Earth from becoming one too. The instruments we have flown past the clouds, and the landers we managed to put on the ground, gave us temperature, pressure, and a short list of chemical readings, but they never gave us a timeline. We know what the surface is today. We do not know, with anything like certainty, what it was 1 billion years ago, or what changed between then and now. The panoramas from Venera 13 and its sister craft remain, even now, the only true photographs ever taken from the surface of Venus. No spacecraft built since has survived long enough, or been sent at all, to add to that record. For over 40 years, the most detailed direct look we have at the ground of our planetary twin has been a handful of grainy frames captured in the minutes before a machine died. Everything else we believe about that surface, we infer. Nothing built on Earth has ever seen through the cloud deck of Venus from orbit, and that fact alone has shaped almost every mission sent there. The clouds sit in a layer roughly 30 to 40 miles above the surface, composed mostly of sulfuric acid droplets suspended in a haze that reflects sunlight so efficiently that Venus is, from a distance, the brightest planet in our sky. From below those clouds, an observer would see nothing of the stars. From above them, we see nothing of the ground. Ordinary cameras simply stop at the cloud tops, which is why almost everything we know about conditions underneath came from radar, landers, or descent probes, rather than photography from orbit. The clouds themselves do something orbital mechanics did not obviously predict. Venus, as a solid body, takes about 243 Earth days to complete a single rotation, one of the slowest rotations of any planet we have measured. Its cloud tops ignore that pace entirely. They circle the planet in roughly 4 days, driven by winds that exceed 200 miles per hour, a phenomenon researchers call superrotation. The atmosphere, in effect, spins many times faster than the world underneath it, dragging that acid haze around Venus in a matter of days while the ground below crawls through its own year at a fraction of that speed. No one has fully explained why the atmosphere moves this way. Researchers have proposed several mechanisms involving heat transport from the day side to the night side and complex interactions between atmospheric waves and the planet's slow spin. And instruments on missions like the European Space Agency's Venus Express and Japan's Akatsuki orbiter were built partly to study this exact question. Even with years of continuous observation from those orbiters, the underlying drivers of superrotation remain a live subject of debate among atmospheric scientists, not a settled result filed away in a textbook. This is the layer that has defeated most of our attempts to simply look. Ground-based telescopes on Earth, however powerful, cannot resolve anything beneath the cloud deck in visible light, because the light our eyes and our cameras use never makes it that far down. Infrared windows exist, narrow wavelengths where the clouds happen to be more transparent, and missions have used them to catch fragmentary glimpses of surface heat signatures on the night side. But those windows are thin, and the picture they offer is partial at best. More a suggestion of shapes than a photograph. What this means, practically, is that every institution that has tried to study Venus has had to work around the same wall. The clouds obscure the surface from every angle we would naturally choose, which is part of why radar became the tool that finally cracked the planet open. Since radar waves pass through the sulfuric haze largely unaffected in ways visible light cannot. It also means the atmosphere itself, the very thing hiding the ground from us, has become one of the central mysteries of the planet in its own right, worth studying independent of whatever lies beneath it. We built spacecraft to understand a storm that never stops, wrapped around a world we still cannot fully see. Radar mapping is the reason we have any coherent picture of the ground on Venus at all, and nearly the entire modern picture traces back to a single spacecraft. The National Aeronautics and Space Administration launched an orbiter named Magellan in the late 1980s, and between 1990 and 1994, this probe used synthetic aperture radar to map roughly 98% of the surface, penetrating the cloud deck in a way no camera ever could. The images that came back were not photographs in the ordinary sense. They were built from reflected radar signal, rendered into shapes and elevations, but they showed us, for the first time, an entire world's worth of terrain rather than a handful of panoramas from a dying lander. What that terrain contains has occupied planetary geologists ever since. There are vast volcanic plains covering most of the surface, smoother and younger looking in places than researchers initially expected. There are mountain belts folded upward in ways that suggest real tectonic compression. There are strange, round, flattened features, nicknamed pancake domes, thought to be volcanic in origin, formed by thick lava that spread outward rather than piling up. And scattered across the surface sit impact craters, relatively few of them compared to older worlds like our own moon, which itself became evidence in a separate argument over how old this surface actually is. The most contested terrain type has a name borrowed from mosaic tilework. Tessera regions are heavily deformed, ridged, and fractured highlands that appear, based on the way they overlap with the smoother plains around them, to be the oldest surviving ground on the planet. Some researchers read Tessera as the remnants of Venus's original crust, possibly even continents, raised and folded during an earlier era before the volcanic plains buried most of the rest of the surface. If that reading holds, Tessera terrain is the closest thing we have to an ancient diary page from a Venus very different from the one we see today. Whether that reading holds remains genuinely unresolved. Radar mapping has a hard boundary built into it, and that boundary sits right at the edge of what these images can actually prove. Radar tells us shape, roughness, and elevation. It does not tell us mineral composition, and it cannot detect water, past or present, in any direct way. A radar image can show us a highland that looks like a folded continent without being able to confirm what that highland is made of, or whether an ocean ever touched it. Every claim about ancient Venusian continents or vanished seas is built on inference, layered on top of shape, not on a direct chemical reading of the rock itself. That gap is precisely why the Magellan Archive, more than 3 decades old now, remains both our most valuable resource on Venus and a fundamentally incomplete one. It is the closest thing we have to a full map of another world's surface. And at the same time, it is a map we can read several different ways depending on which assumptions we bring to it. Nearly everything that has been proposed since about the deep history of Venus, oceans or no oceans, continents or none, rests in some way on how a small number of geologists chose to interpret shapes in decades-old radar returns, because it is still, to this day, the only complete look we have ever gotten at the ground. Somewhere underneath the disagreement over Venus sits a much larger question, one that reaches past this single planet into how we define habitability itself. Climate modeling teams, including researchers at the National Aeronautics and Space Administration's Goddard Institute for Space Studies, have run simulations suggesting Venus may have hosted shallow oceans and relatively mild surface temperatures for as long as 2 to 3 billion years, roughly comparable to how long complex life took to emerge on Earth. In that version of events, Venus was not always a furnace. It was, for a substantial fraction of solar system history, a second habitable world sitting in our own neighborhood, before some combination of increasing starlight and atmospheric feedback tipped it into the runaway greenhouse state we observe now. A study published in the journal Nature in 2021 argues against nearly all of that. Working from atmospheric chemistry and models of how Venus's early crust likely behaved, its authors conclude the planet may never have had liquid water oceans at all, that the conditions right after formation may already have pushed it toward permanent, extreme heat, rather than temporary calm. In this reading, the twin story we tell about Venus and Earth breaks down almost immediately after formation, and Venus was never a plausible cradle for anything resembling life. Not for a moment. Both sides point to the same piece of physical evidence and read it differently. The ratio of deuterium to ordinary hydrogen in the Venusian atmosphere is unusually high compared to Earth, a signature generally associated with a planet losing large amounts of water to space over time, since lighter hydrogen escapes more easily than its heavier counterpart, deuterium. Researchers who favor the ancient ocean model treat that ratio as leftover proof of oceans that boiled away. Researchers skeptical of that model argue the same ratio could result from far smaller amounts of water lost more efficiently without ever requiring an ocean's worth of it to begin with. No one currently has a way to settle which reading is correct. This argument matters for reasons that extend well past Venus itself. If a planet built from nearly the same raw material as Earth, at nearly the same distance from its star, could either sustain billions of years of mild conditions or never have a chance at all, then the line separating a habitable world from an uninhabitable one may be thinner and less forgiving than we have generally assumed. Some researchers now treat Venus less as a curiosity and more as a cautionary case study for what could happen to Earth given a different set of starting conditions, or a different amount of time. The phosphine episode of 2020 showed just how fragile our confidence about this planet really is. A research team announced a detection of phosphine gas in the Venusian clouds, a molecule that, on Earth, is strongly associated with biological processes, and the announcement briefly reopened the question of whether the clouds of Venus might harbor some form of microbial life. Within months, other teams challenged the detection itself, questioning the data processing methods used to identify the signal. And the debate over whether phosphine is present at all, let alone what it would mean if it were, remains unresolved today. An entire cycle of public excitement and retraction played out over a single, ambiguous spectral line, and it settled nothing. What all of this leaves us with is not an answer but a fork. Venus was either a habitable world for billions of years, or it was never one at all, and every dataset we currently hold can be read to support either version. That is not a small gap in the science. It is close to the largest possible gap, sitting directly underneath the question of what actually happened to the planet next door. The only way to close a gap this large is to go back and look directly, and that is exactly what the next mission to Venus intends to do. The National Aeronautics and Space Administration has a probe in development, formally named the Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging Mission, currently targeted to launch before the end of this decade. Unlike the orbiters and radar mappers that came before it, this mission is built to fall. It carries a titanium descent sphere designed to survive entry into the Venusian atmosphere and plunge straight through the cloud deck toward the surface below. That descent is expected to last roughly 60 minutes, from the moment the sphere separates to the moment it reaches the ground. And for most of that hour, its instruments will be working. A mass spectrometer on board is designed to sample the atmosphere layer by layer as the sphere falls, measuring noble gases and their isotopes in far greater detail than any previous mission has managed. Data researchers hope will finally help settle how much water Venus lost over its history, and how quickly. As the sphere nears the surface, cameras are intended to capture images of the ground in the region known as Alpha Regio, an area of Tessera terrain, the same contested highland type some scientists still read as ancient continent, and others read as something far less dramatic. If those cameras succeed, they will produce the first direct images of the surface of Venus taken by any spacecraft since Venera 13 fell silent in the early 1980s. That alone would close a gap in our direct knowledge that has stood for more than 4 decades. It is worth being honest about what a single mission, however capable, can and cannot do. One descent through one column of atmosphere, landing in one region of Tessera, cannot settle every open question about the deep history of Venus. It cannot, by itself, prove or disprove whether oceans once existed there. It cannot resolve the argument over phosphine, since it is not built to search the clouds for biological signatures at all. What it can do is add a real, direct measurement to a body of evidence that has, for a very long time, been built almost entirely out of inference, models, and decades-old radar. If you have ever wondered what it would take to actually know, rather than guess, whether the world next door was once like our own, this is close to the honest answer. It takes 1 hour of freefall through acid clouds, a handful of instruments built to survive conditions that have killed nearly everything we have ever sent there, and years of patient analysis afterward, before anyone can say anything with real confidence. What makes this planet worth returning to is not simply the heat, or the pressure, or the acid. Striking as all of that is, it is the fact that Venus and Earth appear to have started from nearly identical material, at nearly the same time, in the same small region of space around our star, and one of them became the only home for life we have ever confirmed, while the other became one of the most hostile surfaces in the solar system. We do not yet know at what point their histories actually diverged, or how narrow the margin was between the two outcomes. Somewhere in that unanswered divergence sits a warning we have not finished reading, one that concerns our own planet as much as it concerns Venus. Two planets left the same disk of dust and gas around the same star, carrying nearly the same material. And only one of them still carries anyone able to ask what happened to the other. Venus keeps its history sealed under acid and pressure and heat, offering us fragments through radar returns, contested isotopes, and a handful of photographs taken by machines that died within hours of arriving. We built our understanding of a whole world out of those fragments, and we still cannot say for certain whether it was ever gentle. Every answer we eventually get from underneath those clouds will also be, in some quiet way, an answer about the conditions that keep any world livable at all, including our own. Until that descent sphere reaches the ground, the planet next door keeps its history to itself, and we keep watching the clouds, waiting to find out what kind of world we are actually looking at. Watch the next video.